Hi, in this video we're going to have a look at how to use beam elements in SolidWorks simulation. Beam elements can be used when your design consists of parts that are significantly longer in one dimension than the other two. Like in this example, we have a conveyor frame that is made up of steel tubes. In this case, we've used the weldment features in SolidWorks to model our part. The weldment features can be found on the weldments tab in the command manager. If you don't have it, you just right click and add it by clicking weldments. So the principle is that you create some sketches in SolidWorks with just the center lines or some lines for where you want your structural members. And then you go to your weldments and you select the feature structural member. In here you can select what type of cross-section you want, what dimensions, and then what lines to apply this cross-section to. So it's very easy, very fast to get a steel frame like this done. So if you use your weldment features in SolidWorks, SolidWorks simulation will automatically recognize them as beam elements. You don't have to use it, but they will be used automatically for structural members and weldment features. So let's take a look at SolidWorks simulation. So let's create a new study. We can call it static 1, no problem. Click OK. And at the top here, we have our conveyor frame, and below that you have your solid bodies. As you can see, you have a special icon here, little symbol, that is an I-beam, and that indicates that these are going to be meshed with beam elements. If we'd like to change that to use the regular tetrahedrons or solid elements, you can right-click one of them and select Treat as Solid. Then it changes the symbol to indicate that these are going to be meshed with the tetrahedrons. To switch back, you right click and select Treat as Beam. So you can do this for solid bodies that are not created with the weldment features. Then you just right click it, select Treat as Beam. You will get a warning, however, if the length, if the long dimension isn't significantly longer than the other two, then SolidWorks will give you a little warning that perhaps this is not a good approximation and you won't get accurate results. But as long as you're comfortable with running it, it's okay to run it. However, you get a little warning just to be sure. Okay, so let's add some material properties. We can right click here, apply material to all bodies. You can select some steel, perhaps the alloy steel. So let's click apply and close. The beam elements are just lines. So let's have a look at how it's modeled. So here is the conveyor frame we have, and this is how the mesh is represented in SolidWorks. In reality, it's just lines, but they're hard to see on the screen. So SolidWorks visualizes these as cylinder shapes, so that it's easier to see them. But in reality, it's just lines. They have 2 nodes, each element, and each node has 6 degrees of freedom. So they have 3 translational degrees of freedom and 3 rotational degrees of freedom. The rotational degrees of freedom are there because otherwise you can't bend a straight line. If you only have translational, you can just stretch it and compress it, but not bend it. You have to rotate the nodes in order to bend it. So we have to have 6 degrees of freedom. In this picture, every little line on the cylinders is a node. So each element is just this short distance between 2 lines. So that's how the mesh works. If we head back to SolidWorks, you get these pink balls in the graphics. These are your joints where the structural members are joined together. By default, at each joint, there will be a rigid connection between the two structural members, or the beam elements. A rigid connection is the equivalent of welded, as they are welded together. So if we want to change that, you can just right click, for example, any of the solid bodies of the beams, right click it and select edit definition. Then you'll get your red and blue end and how the connection type should be there. The default option is the rigid connection, as it's perhaps welded. Otherwise, you can release some of the degrees of freedom. For instance, if you select hinge, you will release the rotational degrees of freedom in the connection. So then it will be like a rod that's just hinged in place, but it can rotate. It won't transfer any moments or torques. In this case, we want everything to be rigid, however, so we won't change anything. We'll just click OK. So how this works is that SolidWorks calculates a number of different properties for the cross-section of these beams that we don't have to do by hand. It's the bending stiffness of the beams in different directions, and as well as the torsional stiffness of the cross-sections. We can view the parameters that SolidWorks calculates by right-clicking any beam and selecting details. Here we can see that, for example, the bending stiffness in the two different directions are here, the I values. The torsional stiffness or rigidity is the cross-section parameter, not the material parameter, so it's not really the stiffness, the total stiffness, it's just the part that the cross-section contributes to it. And as well as some shear factor, the center of rotations and shear centers, and stuff like that. It's all calculated automatically in the background, so we don't have to do that by hand or anything, or input these values. SolidWorks do that for us. The next step is to make sure that these joints are the way they should be, that the correct beams are joined together in each joint. This is controlled in the joint group. So if you right click that and select edit, then it's by default it's set to calculate and create joints where the beams are touching. If you have, for example, a small distance between the beams, if you have a clearance for welding or anything like that, then it won't find these. So then you can add numbers like a tolerance. So if they're closer than this value, then it will be create a joint there. Afterwards, you click calculate, and the joints will be created. You can then right click any joint to see what beams are joined at that point. If there is a beam missing or there are too many, you can click them to add or remove beams from here, from that joint, until you close the selection box. So the pink balls here indicates that 2 or more beams are joined at that point. The yellow ones are the free ends, so there's no additional beam connected there. It's just the free end of one beam. Okay, so we won't do any changes, so let's click OK. If it wants to recalculate the joints, by all means do that. Won't change anything. So in this calculation we don't have any connections. We only have the beams, and they are connected through the joints, so we won't have any contact conditions or anything like that. So let's move on to the fixtures. So right click fixtures and let's click fixed geometry. So in this case we only have 3 different type of fixtures to select from. It's the fixed geometry that removes all of the degrees of freedom, so all 6. We have the immovable fixture that removes only the translational degrees of freedom. So this can be useful, for example, if the steel frame is standing freely on a floor, then the beams or the legs can be free to rotate but not move around on the floor. So in this case, we will use the immovable or no translation variant. So let's click that, and then as you can see from the symbol here, we can only apply these fixtures at the joints. So we can't like fixate a whole beam or anything like that. So it's just the joints. So let's click these joints on the floor. Let's click all 6 of the yellow balls like that, and then click OK. Okay, so let's move on to the loads. These are a bit special when it comes to beam elements. So right click external loads and select force. So here you can see you have different selections based on how you want to apply your load. You can apply it to a single point. If you would have a vertex on your beam, you can apply it and SolidWorks will map that to a node on the beam. Otherwise, you can select individual joints to apply loads to, or a distributed load on a whole beam or a part of a beam. So in this case, we will start by adding forces to the joints. So let's click that option and then add a force to this joint here. So we have to select the direction because SolidWorks doesn't know what direction a point has or what direction our force should be in. So let's click directional reference. We can select, in this case, perhaps the front plane, because we want to have our force to the side in the lateral direction, or the normal direction to the front plane. So let's select the front plane and then the normal to plane option. So let's activate that and input perhaps 50,000 newtons. Okay, under here, under the force, we have our torques or moments. We can add a moment as well. It's moment around each axis. So if we select the normal to plane direction, it's around that normal vector. So let's click that and you will see the symbol here. You get this rotational disc that indicates that we have a rotating force or a moment. Let's do 20,000 perhaps. The direction, is it clockwise, counterclockwise, is following the right hand rule. So you can just take your right hand, stick the thumb in the direction of the arrow, and then you will get your positive direction of your moment with your fingers. So let's click OK. So that's how you apply forces to individual joints. So let's do a distributed load as well. So right click external loads, click force, and then we select the beam option. So let's click that and apply distributed loads to these 2 beams. What direction? Well, it's the vertical direction, so let's select our top plane for direction reference, and then it's also the normal to plane direction here as well. We can reverse, so it's downwards, and then perhaps 15,000 newtons. You can do distribute loads that are not uniform like this. Then you have your non-uniform distribution. We won't go any deeper into that, but you can select different profiles. You can select different types. You can even do a table driven so that you can change the distribution based on where on the beam you are, or just apply a load on a section of the beam. However, we won't go into depth there. You can check that out on your own. So in this case, 15,000, you can, this is the per beam force. If you want, you can define the force as newtons per unit length. So for instance, per meter beam, if you have the force in that form. However, we want to apply it for the total. So let's click OK. So that's the things that you have to consider when applying fixtures and loads in your beam element simulations. So let's create the mesh. So right click mesh and click create mesh. You won't have any settings here, so you just get your mesh. If you want to change the mesh density or anything like that, you can apply mesh controls as you're used to for these beams as well. Okay, so let's run the study and see how we extract results for beams. So select run. And it's very fast. You can imagine how you would solve this with tetrahedrons. You would need perhaps 1 million elements with tetrahedrons to get the proper accuracy. In this case, we only had, let's right click results and solver messages perhaps. And we have a number of degrees of freedom, 1300. So that's almost nothing. We have 234 elements. That's a very small amount compared to over 1 million. So these are very fast, but you get your the results, as you see, are more of a macro level. So you won't get any detail. For example, if you have drilled a small mounting hole or anything like that, those will be lost because this is more macroscopic level of the structure when you use beam elements. So what you get, the default plot, result plot for the stresses are the upper bound axial and bending stresses. So for beams, we don't have enough information to calculate any von Mises stresses, and the usual the biggest contribution to or the biggest stress in these types of structures are often the bending stresses because of bending, because the beams are often long, so it's dimensioned for bending. And the actual axial stresses and the bending stresses are both normal stresses, so you can just add them together. And the upper bound part means that when you're bending in multiple dimensions, you get different bending stresses for different parts of your cross-section. And when you add some axial forces as well, you will get different stress results for different parts of your cross-section. The upper bound means that we just take a look at the maximum values, so the highest values. So this can be a good substitute for the von Mises stress that you perhaps more used to looking at. The displacement is nothing to consider. You will get the displacement of each node as usual. In this case, like 3.5 millimeters. If we take a look at the other stress results, we can do that by right-clicking on results and define a new stress plot. Here we can select the upper bound, axial and bending. We can also plot just the bending parts in the different directions. So each beam is divided into 2 main directions. Direction 1 is usually the longer part of the cross-section, the longest axis of the cross-section. That is your direction 1, and the shorter one perpendicular to that is the direction 2. So you can also plot torsional or shear stresses, the torsional only and the shear in direction 1 and direction 2. So if torsion is a big part of this, you should absolutely have a look at that, but the usual is that the bending is the main concern. So the upper bound axial and bending is the most important one most of the time. You can render the beam profiles, then it won't be the upper bound axial bending, then it will be just the axial bending, because then we can see the cross section and it can vary. So we can see the differences in different parts of the cross section. So let's try that. Click that and click OK. So here we have our axial bending, and then we can see that we have higher stresses in the top than the bottom. Here we get actual compression stresses, or yeah. So we have tension and compression, so plus and minus. Yeah, this is a bit heavy on the graphics if you have many beams, so take caution. Of course, you can also plot your beam diagrams. So if you want to see the distribution of the bending moments of a beam, you can right-click Results and select Define Beam Diagrams. So let's try this. Let's select the bending moment, perhaps about direction 1, Newton meters. We want to do it for all. Let's select one, and let's select this one. Click OK. And then we can see how the moment, bending moment, differs. So it goes from very large up here down to 0 down here, because that's a free end and we don't have any moments in the floor because it's only immovable. So it's a free end in rotation. Okay, so that's it for this video. Beam elements, if it's okay, that you are okay with the level of detail, it's a very powerful and very efficient way of doing your simulations. Thanks for watching. Bye.